That was the force due to the spring. So we have these three cases that you just saw. Okay. So now we have a third force, which is called damping. And that's given as F sub D. Okay. And this force may or may not be present for a given problem. So this one may or may not be present. Okay, so damping may or may not be present. And dampers work to counteract any movement. And there are several ways to define a damping force. And the one that we're going to use is the following. It's going to be F sub D, and that's going to equal negative gamma times U prime. Okay, where gamma is going to be bigger than 0, and this is the damping coefficient. Okay, is the damping coefficient. Okay. So let's think for a minute about how this force will act. So if the object is moving downward, then the velocity from equilibrium, which is given u prime, will be positive. Okay, so it's going downward, so it will be positive. And so the damping force F sub D will be negative and acting to pull the object back up, right? So let's draw that. If the object is moving downward, right, then the velocity will be positive, right? And so the damping force, which is acting to counteract this, which is F sub D, will be negative in order to pull the object back up. And so likewise, if the object is moving upward, the velocity will be negative, right? And so the damping force will be positive and acting to push the object back down. Okay, so this will be positive. So in other words, the damping force as we define it will always act to counter the current motion of the object, and so will act to damp out any motion in the object. Okay? Alrighty. So now we move on to the fourth force, which are just going to be, generally speaking, external forces. And this is the catch-all force. If there are any other forces that we decide we want to act on our object, we lump them here and we call it good. We typically call f of t the forcing function. Okay, so putting all of these together, this gives us the following for Newton's second law, which becomes mu double prime, which equals mg minus k times L plus u, okay, minus gamma u prime plus capital F of t. So you can see how all the forces come together in this expression. Or you can rewrite this and you get the following, which is sometimes an easier expression to use, which is mu double prime plus gamma u prime plus ku, okay, which equals mg minus kl plus f of t. And you could probably guess why we have it in this form, because now it's set up as a second order differential equation that we can solve, right? So let's explain this a bit. So when the object is at rest in its equilibrium position, there are exactly two forces acting on the object. The first one is the force due to gravity and the force due to the spring. Also, since the object is at rest and not moving, these two forces must be constantly canceling each other out. This means that we must have the relationship that mg is equal to k times L. Okay? And so using this in Newton's second law gives us the final version of the differential equation that we will work with going forward, which is mu double prime plus gamma u prime plus ku, which equals f of t. Okay, so as you noticed, what ends up happening is these mg and kl term cancel out, and we're left just with f of t here as a result of that physical situation. And along with this differential equation, we will also have two initial conditions. Okay, the first one is u of 0 equals u sub 0, which is initial displacement from the equilibrium position. So I'll just make sure I write that down. That's initial displacement. Displacement from the equilibrium position. I'll just say equal for short, and position, or pos for short. Okay. And then of course we have to have u prime is 0 equal to u prime not. And the reason why is because we have a second order diff eq, so we need two initial conditions. And this is going to represent the initial velocity. Okay. And note that we'll also be using this expression back up here, which I'll call equation 1, to determine the spring constant, or K. All right. So next time, on Thursday, we're going to start looking at some specific cases. We're going to also derive some very simple situations for different vibration scenarios, and then begin to solve some real world examples as well. And that'll be it for today's lecture altogether tonight. So please let me know if you have any questions regarding any of the material that we covered this evening. And also, as you're going through these notes, if you wish to see me during office hours, again, that time is between 4:10 to 5:20 every day, Monday through Friday, and you may use WebEx to access me online. And so be sure to create a WebEx account, and if you want to see me online, be sure to log in, and I'll be there to answer your questions. All right, and that's it for us tonight, guys. Thank you. Have a good one.